Okay, so hello everyone, and thank you very much for coming. Today we're going to see a research that we've conducted last year on Qualcomm drivers code for Android. So our agenda for today. First, we will speak about chipset generally, their location in the ecosystem of Android, how they affect how they affect the overall security of Android. Then we will focus more on Qualcomm chipset and review some of its different subsystems. Afterwards, we'll reveal new, not anymore, zero-day vulnerabilities that we found, including a video, a demo of one of them. And finally, we'll discuss some sticking points in the security of Android and ideas how to improve it. So, 30 seconds about myself. My name is Adam Donenfeld. I've been a security researcher for years, mainly in the mobile field, but I've done some PC stuff as well. I've mainly done security assessment and exploitation. Right now I work at Checkpoint as a lead security researcher for Android, and in my free time I also study German. Additionally, I would like to thank Avi Bashan, Daniel Brody, and Pavel Berngolz for helping me and supporting me during the hard moments in the research. So let's talk about Android and the Android architecture. The Android supply chain consists of very few fundamental players we all know. First one is the Linux kernel with a few modifications like Binder, for example. Then we have the Android project, which is exclusively developed by Google, but also third-party contributors send patches and modifications. And we also have the OEMs like Samsung, LG, HTC, Asus, and many others. But that's not the complete list. There is another player that is often underestimated for its effect on the security of Android, the chipset. And the chipset has a very important role in the supply chain of Android for two main reasons. First of all, most of the chipset modifications are usually very essential and in a very low level in the system. And that means that if we find a security bug, it often leads to a game over in the persuasion of privilege escalations in Android. Now, additionally, since chipsets usually distribute their patch and stuff to many different OEMs, it means that a single vulnerability in the chipset code is most likely affecting multiple OEMs, hence posing a very large risk than a vulnerability in just OEM code. Now, let's see. I know that the market is fragmented very equally, and not. We can see here that Qualcomm dominates the market, and it is the most popular ARM chipset manufacturer, and was therefore a very interesting target for our research. So let's talk about Qualcomm. Qualcomm has a very large impact on the overall system. In fact, there are a lot of different subsystems which are completely written by Qualcomm. Each one of these subsystems is a great place to start looking for vulnerabilities. And if the component is low level enough in the whole system, one bug would probably be enough to completely compromise the device. And that's without mentioning components that have been modified to satisfy the requirements of Qualcomm. And let's see an example of one of these. So our first vulnerability, we call it Ashmanian Devil. It's a vulnerability in the Ashman module. Ashman module is the Ashman is Android shared memory. It's a proprietary memory allocator. It is implemented in the file path we see here. It allows sharing memory between processes, and it reminds a little bit the Linux SHM mechanism, except that a few differences, like it supports a file-based API. So the whole usage of this mechanism is by file descriptors. Now, Qualcomm wanted to expand not the functionality, but the API of this mechanism, the kernel API. So it wanted to easily receive information just by getting a file descriptor from the user. And that's one of the functions that Qualcomm added. So as we can see here, let's see, I don't think it works. Okay, so as we can see here, the function receives an input parameter, a file descriptor, and 3 output pointers. And what the function does is converting the file descriptor to a struct file, which is the internal representation of file in the Linux kernel. Then the function checks if it is indeed an hashmem file. And if it is, it just extracts data from the private data of the file, which is the pointer to the pointer to information, and it depends on every type of file. So it just extracts information to the output pointers and exits. Now, a question that each security researcher must ask himself is, how does Qualcomm verify that our file descriptor is indeed an hashmem file descriptor? Now, for those of you who are a little bit less familiar with the Linux API, what we usually have is the way to distinguish between different file types is by the operation handlers. For example, let's take a socket file, an irregular file. If we perform a write operation on a socket file, obviously the behavior is different in comparison to a regular file. Now, again, everything is done by the kernel, so we can just compare pointers, and eventually these handlers are just pointers. So we just compare a pointer, and we can see if the type of the file we think is actually the type we were looking for. But Qualcomm decided that it's boring to do the obvious, and instead of doing that, they checked what's the name of the file. You know, if the file name is hashmem, it must be an hashmem file, no? So let's see what we have here. We need to create a file name called hashmem on the top of a mounting point. Now, why on the top of a mounting point? Because it's /hashmem, and it gets this gets the full path from the mounting point. So unfortunately, / is the RAM disk, and it is just read-only. And any other mounting point is not accessible for the untrusted application. Now, again, if we were root beforehand, we can just do whatever we want, but we are taking into perspective that we are unprivileged at this point. So the way we found to overcome this problem was using a unique feature called OBB. So OBB is opaque binary blob, is deprecated but still works. So a few years ago, if you would have wanted to upload an app to the Google Play, it mustn't be more than 100 megabytes. So let's take, for example, games. Games have textures, sounds, pictures, whatever, and they usually cross this limitation. So what they used to do is first download the main functionality of the app, and then externally download all the graphics and textures. So OBB is basically a file system that anyone can create, externally download, and then just mount it. So yeah, it's kind of fun. So what we did was, first we created an OBB file system, and we put a file called hashmem in its top directory. Then we just mounted it. We don't need any permission for that, by the way. And then we have a file name called hashmem on the top of a mounting point, and we can just send it to the kernel and have fun. Okay, now going to the next example in a completely different module, again, by the masterpiece. About the disclosure, and this is a very important point during the presentation. We reported the vulnerability back in April, and Qualcomm confirmed that it is indeed a vulnerability a month later, which is reasonable. And then they released a patch in 28th of July. But even though it was public since the 28th of July, there was a public advisory, Google fixed it only in the 6th of September. So everyone in the world had more than a month to see the vulnerability, exploit it, and steal data and do hacker stuff. So going to the next vulnerability in a completely different module. So this one is the IPC router module. It is an IPC mechanism that was written by Qualcomm. It should not be accessible from an untrusted application. and it is not accessible now, but it was, and Google just added an SE-Linux tool to block it. So this IPC mechanism is just a socket address family, number 27, AF-MSM IPC, and you can just send and receive messages to other sockets in the family, in the address family, but it has a few cool features that we are going to see. First, for example, you can whitelist or blacklist sockets based on group IDs, which is very interesting if you want to prevent unprivileged processes from talking to you. And another feature that we're going to go deep and see it is monitoring the system. Anyone in the system could just monitor creation or destruction of these endpoints, and it's very cool in my opinion. Now, the best thing about it required no permissions to use. So there are 4 types of these sockets: client port, control port, IRC port, and server port. We are not going to talk about IRC port and server port because they required high permissions to use. So each time we create a socket, it is by default a client port, and client port is just a socket that can send and receive data. And if we wanted the control port, we had to issue an ioctl, and then our client port will be converted to a control port. Now, how does this look in the kernel? This is the function that handles ioctl requests. It's very restrictive and straightforward. Every time you issue an ioctl on the system, it locks the socket, so we cannot issue 2 ioctls on the same time on the socket. And according to our request, it does stuff. So if we issue IPC router ioctl bind control port, our socket will be converted from whatever it is to a client port. That's the code that converts the socket. When I say convert, it just means take a socket from a list A and move it to list B. Now, a second, because the laser doesn't work on the screen. Wait. So this is just a lock to the client port socket, to the list. Then we take the object out from the client port list. We unlock the socket. We unlock the list. We lock the control ports list. We add our object to the control ports list, and then we unlock it. Pretty straightforward, but there is a vulnerability, and we are going to see it now. It's kind of hard to follow, but we really try to make it as clear as possible. So we are going to convert this object to a control port. So the first line, the first command is to lock the client list. And then we take the object out from his list. And now it's not in any list. Then we unlock the client list, we lock the control list, we add the object to the control list, and we unlock it. Not so complicated, and there was nothing wrong with the flow that we saw here. But, there's always this but. What happens when we convert control port to a control port? There's no limitation for that. So let's examine the code. We lock the client list, we take the object out from his list, which is not locked. We unlock the client list, locking the control list, putting the object back, and unlocking the control list. Now, for those of you who missed it, even though the control list is unlocked, we modify it. And fun stuff can happen. So what do we have here? Or what is our primitive? The control port list is modified without a lock, so we can delete 2 objects simultaneously, and therefore there is a race condition here, which leads to ease of the free. Now, yeah, I love the animation too. Anyway, there is an explanation of how to exploit it to achieve full root capabilities, but because we added some stuff, we are going to skip it, but you can find it online or ask me later. Now, demo time. So what we're going to do, because we found it back in the end of 2015, we are using Marshmallow in this case. So we are just installing our POC. We are going to see now that the device is not rooted and that it is indeed a genuine kernel version, and that it is a Marshmallow device. We can see it here, our build version release. And we are not rooted, of course. So there are no prerequisites. SLinux is enforcing, and we are not running as root. Okay, so our PLC ultimately installs a suite file in the system partition, and it also creates a local service at port 1337 that just receives text and issues this text as root commands. So it's basically netcat and then system and put it, just call the command. So we're going to see now that system is normal. There's nothing suspicious there. And that's our service at port 1337 is just not there yet. Great. So now we're going to actually exploit the vulnerability. It takes approximately 3 seconds to do that, but because the GUI, do also stuff, it's maybe 6 seconds. Okay. So the suite file that we are going to place in the system partition is called Zugang because of my love to the German language. So we're going to see a Zugang file, which is a suite file, and we're going to see that the service is up. We are now root. The entire, 3 seconds, but cleans up some stuff. Okay. And this point, the device, the suite file is placed, the service is up, and now we're going to see the difference. You're still not running as root, but SLinux is no longer enforcing the system. And we're going to see now that if we try to connect to 1337, we're no longer getting connection refused. And if we see the system partition, we see that we have a Zugang file at the bottom here, and it is a suite file. And we can read the fstub, which is only accessible to root processes. Again, we just connect to the service, and we are running as root. Who am I think also. Yeah. Cool. So that was a demo, 3 seconds to exploit. And again, for more details about how we did that, just come and ask me after the presentation. Another very disappointing point about the disclosure process of this vulnerability. We reported it back in the beginning of February 2016. A week later, Qualcomm confirmed the vulnerability and released a patch in the end of April. When I say released a patch, I mean a public patch, so everyone can see the vulnerability. But still, it took 4 months. 4 months till it was actually fixed on the most flagship devices of Google. So 4 months for hackers to exploit it. And nothing prevented them from doing this. Okay, another case. But now before we go to the next case, we have to talk 30 seconds about a mechanism called IDR. So IDR is a Linux kernel mechanism. It allows mapping between safe IDs, that's how I call them, safe IDs and kernel objects. We need that because if we want to give the user mode a handle to some object, we don't want to reveal the kernel address for that. So we just use this mechanism. So how it works in de facto, the user wants to create an object, a kernel object. The kernel allocates data and initializes an object. So it has a kernel address, but we don't want to reveal this address to the user. So we just pass this address to the IDR mechanism. The IDR mechanism now maps between this kernel address and just a safe number. And this safe number is returned to the user. And every time the user will want to reference this object, perform comments on it or whatever, it will just send the kernel this number. So it's very easy to use that and very, I think, very useful. So with that said, let's see the last module that we're going to see today, 2 vulnerabilities in this module. The model is called KGSL, or Kernel Graphics Support Layer, written by Qualcomm to support some graphic stuff and vulnerabilities. It is a wrapper to the GPU driver, the Adreno driver, and it communicates with the user mode to render graphics. Now let's see the actual attack surface here. First of all, it is accessible for any unprivileged application, even now, because it's graphics, and graphics are cool, and everyone loves graphics. So we open it using just opening a device called KGSL -3D0. No permissions are needed, and it has 26 ioctls, which are wrappers to the Arduino driver. So let's see how it looks. This is just a part from the table I took from the ioctls table. I showed it for brevity, but you can see that it's very simple to find the appropriate function from the ioctl. Let's take, for example, draw ctx create, which creates a new context in the system. We see that this function receives a command and data. Data is completely controllable by the user. It is not the user mode address, but it is just copied from the user. And we see that eventually it takes the flags from our user parameters, and it calls another function called draw ctx create in ftable. What is ftable? Ftable is the Arduino function table, and we can see that there is a corresponding function from the ftable from here to here. And eventually all the functions that we have in KGSL are just wrappers to, most of them are just wrappers to the Arduino func table. And to convince you that this is a very unsafe mechanism, the two vulnerabilities that we found we didn't even have to go to the Arduino driver. They were just in the wrapper in the wrapping of the user mode parameters. So our first vulnerability, we call it syncoca root. The vulnerability is in an object called sync source. It is used to synchronize between the GPU and the currently running application. Apps don't use it themselves. It is usually wrapped by other graphic engines like OpenGL and soon by WebGL 2.0, which means we could have 2 years late. If we would find it in 2 years, we could have had remotes to the kernel from the web. Now, we don't have to know a lot about the object to understand the vulnerability. We just have to know how to create it and destroy it. And as we saw before, with the IDR mechanism, this object is referenced by this safe ID. So that's the function that destroys the object, that cleans it up. As you can see here, the user, as I said before, the user controls the data pointer. So the user controls this param ID. And what this function does is first checking whether this is a real object in the system by calling KGSL sync source get. And then if there is a sync source, it drops the ref count twice. Why twice? Once for the creation and once again because this also takes a reference. So how does it look? Let's say that the reference count of the object is 1. This function increases the ref count by 1. So now the ref count is 2. And then it is dropped once for the creation and once because we took a reference here. And then the object is freed. But these 6 lines of code are vulnerable to a race condition. There is no pending check, and there is no check that the object is about to be freed. So what happens if 2 threads call this function on the same time? We have an object with the ref count 1, and we just call this destroy ioctl with the same ID, 2 different threads. So first, the ref count is increased to 2. Then the ref count is dropped back to 1. Then there is a context switch. Thread B also increases the ref count by 1, drops it again. Going back to A, the ref count is dropped to 0. And at this point, the object is freed and reclaimable by any of your favorite heap kernel spraying techniques. But thread B is not done yet. So we are going back to thread B, which now drops the ref count on freed memory. So here we can either just drop a ref count for one of our objects, or we can get the system to destroy a different object and maybe control the destruction flow to get code execution. Now again, to summarize it, a very simple vulnerability. We create a sync source object. We know the IDR number. 2 threads destroying the IDR, this object. The ref count is reduced to -1. And just afterwards, once it is on 0, we can just spray the kernel memory and heavy users for free. Okay, disclosure. So here it was reasonable. We reported it in the 4th of April. 1 month later, Qualcomm confirmed the vulnerability. 1 month later, they released a public patch, and on the same day, Google deployed it to their devices. Not the best, sorry, not the best case, but reasonable. Okay, now the last vulnerability, and the same mechanism, again, the KGSL mechanism, we didn't even get to the Adreno one. The last vulnerability is called Kangaroo. The vulnerability is in mapping between user mode data to GPU data, so the GPU memory, sorry. Each time we map data, it is referenced by the IDR mechanism, and an object that represents our mapping is also created. It represents the range of the mapping, the protection level, ref count, and other not interesting stuff. So after we found Syncocca root, we said, okay, let's go to the cleanup function. Maybe we can also find a vulnerability there. And then we saw this again. You can see the user controls the data, and again, there is an ID for the IDO mechanism, and we see that if there is an entry, it just cleans it up. Now we were happy because we didn't see any spin lock or something like that. And then we went to shared memory entry, and unfortunately they were right this time. So here, every time we call a destroy on one of these objects, first atomically it gets some field and swaps it with with the opposite value, and then only once it drops the ref count twice. And again, since this function takes the ref count on the object, it is dropped here, but it will only be cleaned up once. So they lock it appropriately, and no vulnerability here. And in desperation, we said maybe the allocation function is vulnerable somehow. And then we went to the allocation function. So the way we map the data, first we initialized the objects, the objects that represent the mapping. Then they call KGSL mem entry attach process. Entry is the object that represents the mapping. And then it first associates it with an IDR number. Then it just maps it to the process. And here, just like before, we didn't see any spin lock. And there's a problem, because if we call at this point after the IDR alloc, this object is already referenceable from other threads. That means that at this point we can already call the cleanup function, and then this entire code, right, I have no mouse here. This entire code is going to call to use the entry object, even though it might be already freed at this point. So let's see the normal use case of this object. First of all, thread A maps data to the GPU. So the kernel allocates object to represent this mapping. Then it associates it with an IDR number, with the IDR value. Then it initializes the object. Then if you want to unmap this memory, we just call the release IRTL. The kernel checks whether this ID is already in the system, and if it is, it simply frees it from the kernel. But as I said before, if this is our current situation, we know that our next number is going to be 6 here. So we can call on the same time map and unmap. So first we just map data, an object is allocated, it is mapped to the IDR items, but then we unmap the data before it is already initialized. So the kernel checks whether number 6 is already in the system, and since it is already in the system, it just frees it frees the memory, like K3. And at this point, this is a reclaimable data. We can spray the kernel heap and catch it, but thread A did not finish yet, and now it will operate on free data, which we control and we can manipulate to elevate our privileges and compromise the system. So again, summary of this vulnerability. First, we map memory. Then we know which IDR number we are going to get. So we are going to issue a mapping request and unmapping request on in the kernel on two different threads. And before the mapper thread is done, returns from the kernel mode, we are going to have use after free case in the function on the entry parameter. And a picture of a drunk kangaroo. Okay, again, disclosure procedure. We reported the vulnerability on the same time in the 4th of April to Qualcomm, and they confirmed it on the 2nd of May. And Qualcomm released it on the same time with Syncoca root on the 6th of July, but for some reason, Google fixed it only one month later on the 1st of August. Why? We don't know why. Now, we created an app in Checkpoint that checks whether you're vulnerable to any of these vulnerabilities. More than 500,000 downloads happened in just 1 month. And we got some users could opt in to send us some anonymous data. The statistics were taken in mid-August, and at this time all the vulnerabilities were already public. And that's the information we saw. So 63% of the devices were vulnerable to at least one of these vulnerabilities. Again, this reveals a very bad situation where classic use after free vulnerabilities are public while not patched on most of the device in the world. We take here into consideration device into these statistics, devices that were not vulnerable from the first place, like MediaTek devices that didn't have the Qualcomm code. So the number of the vulnerable devices that successfully received the patch is probably even lower. Next interesting information, number of vulnerable devices for each vulnerability. This is the first one we saw with the Ashman. These are the two KGSL vulnerabilities, and this is the one with the IPC. As we can see, even though we reported the vulnerabilities back in April for these three, for the Qualcomm one, the IPC router was reported in February. Still half a year later, almost half of the market is vulnerable to the Qualcomm vulnerability. Again, I mean, it's not supposed to be. It doesn't supposed to take so much time, especially when public patches by Qualcomm are already available. And the last piece of information. This actually doesn't have to do with the 4 vulnerabilities we saw here, but we can see just, and this is just based on more than 500,000 devices. In mid-August, less than 10% of the market had the latest patch. And if we look just to May 2016, we see that if you look 3 months before August, we see that most of the market did not even receive the security patch. Now, it just means that, I mean, this has to be changed, all this entire patch mechanism. And with that said, suggestions. First of all, the supply chain of Android actually prevents security patches from being distributed efficiently to the endpoint user. A chipset vulnerability is extremely important in that case because every vendor has to adapt and to distribute it on his own. Secondly, sending security patches to the device once a month is not ideal. Once a device is vulnerable, the attacker doesn't necessarily have to exploit the vulnerability again and again. Out-of-band patches are seen often in other platforms like Windows and even by iOS, which is also a mobile platform. And finally, I want to address something that appeared a lot on the media following the release of this research. Verify apps. So while Verify apps doesn't harm your device, it requires a lot of collaboration with Google to work appropriately. prior to the publication of these vulnerabilities, Verify apps did not, or any other built-in mechanism, security mechanism in Android, did not detect any of these bugs. It takes a lot of time and nice amount of effort to actually distribute these protections to the devices, and it required Google to have collaboration with us. So Verify apps is not a magic mechanism that protects us. It requires a lot of work to actually prevent new threats. That's it. I hope you enjoyed the presentation and got some new insights. If you have any question about anything, since this is the last presentation for today, we'll do it outside because the people at Black Hat have to clean up the room. Thank you.